Hello, so for this video we're going to look at starting from the spherical equation for the transport of a molecule, considering reaction rates that you encounter in biological systems for molecule A coming into contact with molecule B to form reversibly a complex between the two, a dimerization reaction. This second order reaction, because you have two reactants that forms a product, so it's nonlinear. And what else can I say about it? This is very common in like receptor and ligand systems, where you're having a signaling molecule bind to a chemical surface receptor. And before we've given you rates, but now you can have an idea of what the limits are for these rates. So upper limit for formation, of something requires a number of steps, and you can determine what some of these upper limits are based on the distance between the molecules, the diffusion rate of them, because you can't have a reaction take place faster than the molecules can find each other by diffusion. Also, it comes into play here is dimensionality. So is this a reaction that's taking place in bulk, or is it between two things that are attached to a membrane? For instance, binding between receptors on a membrane, they have limited degrees of freedom of movement. It's not full 3D. They're moving in 2D all of a sudden. So let's start with the simplest case. Suppose ligand is diffusing towards a large non-diffusing receptor. Okay. What does this mean? It means that the diffusion of the receptor is much, much, much less than the diffusion of the ligand. Okay. And with this starting point, how do we calculate rates for this process? Let's start by determine concentration. Because as the concentration increases, the rate should go up. Okay. 2, determine fluxes, like how fast can the molecules move. And 3, relate fluxes to reaction rates. Okay. And through this, we can determine the upper limit for a reaction rate based on how fast molecules can move in to each other. Okay. So for starting, we can calculate fluxes by calculating distributions. So 1, that's a 1. Okay. Look at steady state. Diffusion for a reaction in 3D. dl over r squared. Over r squared. Okay, there we go. This Apple Pencil was running out of ink. It seems to be working much better now. dl over r squared d by dr of r squared dcl dr equals 0. This is ligand concentration. Okay, and we're going to center our system at receptor. At the receptor. Okay, and the receptor has radius r equals rr. This is radius of receptor. This is a spring term, but if it was fall term, it'd be great to align this lecture with International Talk Like a Pirate Day because of all the instances of r's. So this means that at r equals rr, cl equals 0. What we're assuming here is that at the receptor, it's bound. As soon as the ligand hits the receptor, it's bound, which makes the concentration right at that point in space suddenly 0 because it can't exist there without being bound. When it's bound, it's converted into another type of label. It's converted into the complex. So this becomes boundary condition 1. Okay, and then a long ways. Okay, long way. Let's say a very long way from the receptor. Let's say the radius away from the receptor approaches infinity. CL is going to be equal to CL0. This is just some bulk concentration. This is the concentration that you would use in your simulation of a reaction between a ligand and receptor. So the first thing we're going to do is solve for CL. Okay, we have d by dr, r squared, dCl dr equals 0. So we have r squared dCl dr equals C1 when you integrate it once, right? You can just move this to the other side, integrate it once, you get a constant. Okay, so we're going to integrate again, but you have to do this by moving r squared and dr to the other side. So we have now dCl, the integral of that is equal to C1 over r squared dr. So apply boundary. So you solve this again. You end up with minus 1 over r because it's r squared. You can rewrite this as C1r to the minus 2. If that helps you think about how to do the integration. So then you apply boundary conditions, and you end up with a solution of CL equals CL0 times 1 minus r over r. We've done many problems with many boundary conditions. The process is exactly the same. I encourage you to do this boundary condition determination on your own and end up with this equation. If you have any questions, feel free to contact me. Okay, so this is the concentration. So what? What do we do with this? So this is the concentration. So what? Well, we have to think about the rate of binding to receptor. Is going to be K plus times the bulk concentration, where K plus is the reaction rate. So now we have a distribution, we have a diffusion coefficient, we have a bulk concentration. This is the unknown. This is the reaction rate. What is the upper limit for this reaction rate? So how do we do this? Well, remember, the area of sphere where the receptor is 4 pi r squared. Okay. 4 pi r squared. And the rate then is going to be equal to area times the flux. Okay, the area times the flux is going to be equal to 4 pi r squared, which is the total of all the different approach angles that the ligand can take to the receptor, times our flux term there, Ji. Okay, so we have this. Now recall that we're interested in the normal flux, and so then this normal flux is n, the normal vector to the surface of the sphere, dotted with Ji, which is actually a vector, which is equal to minus Ni, dotted with, because it's pointed outwards, minus dl gradient of Cl, concentration of our ligand. We've solved for the concentration of ligand already. So this is as simple as plug and chug. So we care about is the magnitude. This is just vector notation in case you're doing vector calculus on this, but it's all symmetric, so we can just not worry about it. We have Ji equals, okay, dl, the diffusion of the ligand, gradient of CL0 times 1 minus the radius of the receptor over r. this is the solution that we had earlier for our equation. So, and this has to be calculated at position r. So what's the derivative of 1 over r? It's negative 1 over r. It's actually just 1 over r squared. So we have to do this. This is the gradient operator. This is a derivative. So we have here now, we can rewrite this as ji equals dl cl0 times rr over rr squared. Okay. Okay, so then what does this give us here? This is equal to dl cl0 times 1 over rr. And we have to do the equality between this and our k positive. So if we have the CL0 here, before we had the rate was going to be k, if you recall, was the rate was k plus times CL0. Well, we have CL0, so the overall rate is going to be this. CL0s will cancel out, but we have to recall that the overall rate is the area times the flux. So this becomes 4 pi rr squared times dlcl0 times 1 over rr, or the k plus is then equal to 4 pi radius of your receptor times the diffusion of your ligand. This is, right here, the upper limit for bimolecular interactions. This is the upper limit for bimolecular interactions. It's incredible how often this upper limit is approached or even attempted to be bypassed in simulations and models. This is with one immobilized molecule, with one that's mobile, plus one diffusing. Okay, so this is a very good place to kind of think about and grow from in terms of your understanding of what some of these rates are. So if we go back to this, what does this mean in terms of units? The units, do they make sense? So this is the upper limit for second order reactions. The units of K plus are length cubed over quantity times time, or this could be concentration. So this gives us a concentration. This is quantity. And we always know that second order rates for the balance have units of 1 over concentration time, so this makes perfect sense. So let's see, what else can we talk about with this model here, with this equation? This gives us, if you assume like a diffusion of the ligand is approximately 10 to the minus 6 to 10 to the minus 7 centimeters squared per second. What we can do with this is that, and the radius of receptor, let's say, is about 2 nanometers, okay? We make the substitution, we find that K plus is approximately 10 to the 7 to 10 to the 8 per molar second. This is the upper limit. If you're reading a paper, you're studying a biological system, and you see a rate that exceeds this after you do your unit conversions or whatever else, it can't go past this. Anything past this is not physiological, it's not meaningful. Similar derivations you can easily get for the rate of loss. So you can calculate K minus. And this is a very simple situation. We start with the same place. We start with dl over r squared, d by dr of r squared dcl dr. equals 0. Start at the same place. Same equation applies. Except that now, as this is the amount of unbound or free ligand leaving the receptor, so looking for the off rate, the reverse rate. So as the distance tends to infinity, the concentration of released ligand goes to 0. So suppose you have a bound up receptor and you put it into a bath where there's no concentration of ligand that isn't bound to the receptor. And right at the surface of your receptor, radius of your receptor, Cl equals Cl0. So this equation set right here forms the PDE basis to calculate the off rate, the K minus upper limit. So what do? We do the same exact thing we did before. First you solve it. You solve this equation, you end up with d by dr, r squared dCl dr equals 0. So then you integrate this once, r squared dCl dr equals a. Then you integrate it again, and you get Cl equals minus a over r plus b. Substitute in the boundary conditions for solving for a and b. When you do this, you find that a equals minus c. That looks like an L, but it's a c. Cl0 times the radius of receptor, and the overall equation is simply the concentration of ligand equals Cl0 radius of receptor, all divided by your position r as you go away from your source, from the receptor. So the overall rate of loss is going to be equal to K minus Cl0 times V. That's going to be the total mass loss. And you'll recall that because it's happening on an entire sphere, we have to calculate this overall flux, which is Ji at r equals rr times 4 pi surface area of our sphere, 4 pi rr squared. This has to be equal to K minus Cl0 times 4 thirds pi r cubed, because that's the whole volume of the sphere where this is emanating from. Okay, so then you take the derivative. This becomes minus dl to partial Cl partial r at the radius of the receptor for that derivative, and you end up with after that substitution 4 pi radius of receptor squared times dl, the diffusion of the ligand, times Cl0 times r to the minus 1 equals K minus Cl0 4 thirds pi r cubed. Okay, so pi's cancel out, Cl0's cancel out, some of the r's cancel out, end up with K minus equals 3dl over rr squared. This is the upper limit of your reaction rate constant for the release of molecules. Typically, this is a very high rate, and so it's not something that you'll ever encounter with. This sets an upper limit for the release of a molecule of between 7.5 to times 10 to the 6th to 7.5 times 10 to the 7th per second. Okay, so this is just, it's pretty fast, and most things in biology are stickier than that. But you do oftentimes run into situations where your model will only work better when you want a very high rate of binding. So this is the one you got to watch out for.